What if the universe is not as solid as it feels? What if the rules we trust, time moving forward, causes preceding effects, matter staying put, are only habits of perception, not laws of nature? Every civilization has built its understanding of reality on what seems reliable. The sun rises, objects fall, actions lead to consequences, memory moves in one direction, from past to present, never the reverse. These patterns feel so stable that questioning them once seemed pointless, even absurd. For centuries, physics existed to confirm common sense, not challenge it. Then, quietly, something changed. It did not arrive as a single revelation or dramatic announcement. It emerged in laboratories, in careful measurements, in results that refused to behave. At first, these anomalies were treated like errors, equipment flaws, statistical noise, misunderstandings, but they persisted, they repeated, and slowly, reluctantly, scientists began to realize that the problem was not the experiments. The problem was the story we were telling ourselves about how the universe works. The story said, reality was made of things, solid particles, definite positions, predictable paths. The new evidence suggested something far stranger, that at the deepest level, reality behaves more like a question than an answer. In the early days of quantum physics, this strangeness could be ignored. The effects were tiny, confined to the scale of atoms and photons. The macroscopic world, the world of people, memory, and meaning, seemed safely untouched. Quantum weirdness could be filed away as a mathematical curiosity, irrelevant to everyday life. But the boundary never held. As experiments grew more precise, the anomalies grew bolder. Particles appeared to influence one another across distance, without crossing the space between them. Events seemed to depend on measurements made after they had already occurred. Objects behaved as if they occupied multiple states at once, only choosing a single outcome when observed. Time itself began to look less like a flowing river and more like a landscape, one that could be entered from unexpected directions. Each result, taken alone, could be rationalized. Together, they formed a quiet but devastating pattern. The universe was not merely strange, it was internally inconsistent with the way humans instinctively understand existence. And yet, there was no sense of chaos in the data. The equations worked. The predictions held. Quantum mechanics, as unsettling as it was, became the most successful theory ever devised. Its accuracy was undeniable, even as its meaning remained elusive. This left science with an uncomfortable paradox, a framework that functioned flawlessly while refusing to explain itself in human terms. What does it mean when observation alters outcome? When information appears to travel without time? When the distinction between past and future, here and there, observer and observed, begins to dissolve? These are not questions of mysticism. They are not metaphors. They are the unavoidable consequences of experiments repeated across decades and continents by researchers who set out to prove reality stable and instead found it pliable. Behind every dataset was a human moment, a scientist staring at a screen, recalculating, checking assumptions, feeling that quiet disorientation that comes when the universe stops behaving as expected. No alarms sounded. No laws were officially repealed. Reality simply grew less cooperative. This series is not about disproving science. It is about following it to its edge. Across the next chapters, we will revisit moments when certainty fractured, experiments that forced physics to abandon intuition, discoveries that blurred the line between measurement and meaning, not as declarations of truth, but as invitations to sit with uncertainty, to question inherited assumptions, and to consider whether reality might be deeper, more relational, and more human than we once believed. If the universe is not fixed until it is observed, then perhaps the most important question is not what reality is, but how we participate in it, and whether we have been listening closely enough when it tries to answer back. It started with a beam of light, innocent, silent, ancient in origin. In 1999, a team at Johns Hopkins University, led by physicist Yoon-Ho Kim, aimed a laser at a double-slit apparatus, the same device that had haunted physics since the early 20th century. In the traditional version of the experiment, particles like photons behave like waves when unobserved, creating interference patterns as if they travel through both slits at once. But the moment you observe them, they collapse into particles, choosing a path, obeying classical expectations. Kim's team introduced something new, a quantum eraser. At first glance, it seemed like a minor adjustment. After the photons had already been detected, after their positions were recorded, they passed through an additional apparatus capable of erasing or preserving which-path information. And then, the impossible happened. Changing the experimental conditions after detection somehow changed what had already been recorded. Patterns on the screen transformed retroactively. Photons that had struck the detector and behaved like discrete particles now displayed interference patterns, ghostly fingerprints of wave behavior, as if they had always moved through both slits. The choice to erase or not erase information, made after the photons had done their work, rippled backward in time. How could a future decision alter the past? Physicists scrambled to replicate the findings. The University of Vienna, MIT, and CERN each confirmed the same eerie result. When the quantum eraser was triggered after detection, the past behavior of the photons adjusted to match the new context. Reality didn't just depend on measurement. It seemed to rewrite itself to remain consistent with future observations. Causality, once the unshakable spine of science, appeared negotiable. Dr. Anton Zeilinger, one of the foremost experimental physicists of the era, described the results as a fundamental revision of time itself. Classical logic insisted that the past was fixed. Quantum mechanics, it seemed, disagreed. Some argued that the photon's behavior wasn't literally changing retroactively, but rather that the entire system, including past, present, and future, must be considered as a unified whole. The timeline wasn't a line. It was a loop. Others wrestled with deeper implications. If outcomes depended on future measurements, what did that say about determinism, about choice, about the role of conscious observation? The experiment didn't just shift a scientific model, it shook a philosophical foundation. It suggested that the world might not exist in a complete state until it's viewed in a particular way, even if that viewing happens after the fact. And it raised troubling possibilities. If the future can influence the past, is history a story still being written? Are there moments in our lives, decisions, emotions, encounters, whose meaning hasn't yet stabilized because something ahead has yet to occur? Or are we always entangled with events not yet realized, co-authors of a timeline we mistake for immutable? The delayed choice quantum eraser leaves no easy answers. It offers a glimpse into a universe where time is not linear, where information is not confined by direction, and where what is real may depend on what is known. And in that strange light, we are not just observers. We are participants in a reality that waits, subtly, silently, for our decisions to give it form. It began with a silence, 1.3 kilometers of empty space between two detectors, waiting to betray a truth. In 2015, physicists at the University of Vienna set out to test a question that had haunted science for nearly a century. Is the universe truly local and real? Local meant that objects could only be influenced by their immediate surroundings. Real meant that things had definite properties whether we measured them or not. These ideas weren't just philosophical, they were the very assumptions upon which classical physics was built. Einstein had clung to them like a lifeline. He called quantum entanglement spooky action at a distance, and believed that the strange predictions of quantum mechanics must be incomplete. Hidden variables, he insisted, unknown factors, would one day restore order. But Bell's theorem, developed in the 1960s, gave physicists a way to test the claim. If hidden variables existed, then certain statistical correlations between entangled particles would never exceed a defined threshold. If quantum mechanics was correct, they would. The Vienna team ran the experiment under the strictest conditions ever attempted. Entangled photons were fired toward detectors more than a kilometer apart. The settings on those detectors were determined by random number generators at the last possible instant, so the particles couldn't cheat by knowing what was coming. The results were clear. The correlations between the particles shattered Bell's inequality by 11 standard deviations. The odds of this being random chance were less than 1 in 100 billion. It was no longer possible to pretend. Either the universe allows instantaneous influence across distance, or particles do not have properties until measured. Locality or realism, one of them had to go. Dr. Anton Zeilinger, again at the forefront, declared Einstein's local realism is definitively false. Not theoretically, not hypothetically, empirically. It was a moment both exhilarating and unsettling. Quantum entanglement, once an abstract oddity, had become an unavoidable reality, and what it revealed was staggering. When two particles become entangled, their states are no longer separate. Measure one, and the other responds instantly, no matter the distance. It is not that information travels between them, it's that they are not two things at all, but one system, stretched across space. It's as if the universe forgets where one particle ends and another begins. Physicists around the world replicated the experiment. MIT, the National Institute of Standards and Technology, all reached the same conclusion. Reality at its core is non-local. What does this mean for us? It suggests that the separateness we experience, me and you, here and there, now and then, is not fundamental. It is a scale-dependent illusion. Beneath it lies a realm where everything is connected, not metaphorically, but literally. A place where distance dissolves and properties emerge only when asked for. The implications go beyond physics. They challenge our sense of identity, our stories of agency, even the nature of consciousness. If particles remain undefined until we look, what does that say about the act of looking? If connections persist without contact, what does that say about presence? And if classical reality simply doesn't exist at the quantum level, as Zeilinger put it, then perhaps our daily certainty, the solidity of a table, the reliability of a fact, is a carefully constructed mask, a surface painted over something stranger, deeper, and more mysterious. The universe, it seems, does not wait for permission to connect. It already is. Imagine standing before a wall and then, impossibly, appearing on the other side without climbing, breaking, or passing through it. In 2019, researchers at the University of Toronto asked a question that sounds almost childish. How long does it take for a particle to tunnel through a barrier? Quantum tunneling had been known for decades. Electrons, for example, can appear on the other side of energy barriers they shouldn't be able to cross. Classically, it's like a ball rolling uphill and ending up on the other side without ever reaching the top. No one knew how long the process took. Did the particle pause inside the barrier? Did it slow down, speed up, or did time behave differently altogether? To find out, the Toronto team used attosecond laser pulses, light bursts so short they could measure motion on the scale of billionths of a second. They aimed them at hydrogen atoms, watching electrons as they tunneled. The result? Tunneling took no time at all. Within the limits of their instruments, the particles simply vanished on one side and reappeared on the other. There was no delay, no trace of motion through the barrier. As far as anyone could tell, the electrons skipped over the rules entirely. It was as if space, the terrain we assume every object must traverse, had become irrelevant. Dr. F.M. Steinberg, who led the research, put it bluntly. The electron doesn't seem to spend any time inside the barrier. It's as though reality edited the transition, leaving no footage between before and after. Independent labs in Germany and Switzerland confirmed the findings. Different methods, same paradox. This violated more than intuition. According to special relativity, nothing can exceed the speed of light. But if a particle can appear across a distance in zero time, its effective speed becomes infinite. Physicists scrambled for interpretation. Some argued the particle never really passed through the barrier. Instead, it existed in a state of superposition, on both sides simultaneously, until measured. Others proposed that time itself might be different inside the barrier, not flowing as we know it. But the deeper conclusion was harder to avoid. Motion, as we experience it, might not be the only way things move. What if travel doesn't always require transit? What if connection can exist without continuity? Quantum tunneling is not rare. It powers nuclear fusion in stars, electronic behavior in semiconductors, even chemical reactions in the body. The universe runs on shortcuts we barely understand. But this experiment transformed tunneling from a weird effect into a philosophical question. Is space a solid framework or a suggestion? Is time a river or a filter? And when we think of progress, of effort, journey, cause, and effect, are we mistaking narrative for necessity? The electrons didn't care about barriers. They followed rules we hadn't written yet. And perhaps, beneath the friction of daily life, something in us remembers what it means to move without passing through, to arrive without traveling, to be transformed without delay. The universe, once again, whispers a secret, that the distance between here and there may be far less than we think, or that the walls we face are not as real as they seem. It began with silence, two metal plates suspended in vacuum, unmoving, untouched, surrounded by nothing but empty space. In 2020, a team of physicists at Griffith University in Australia attempted the unthinkable, to detect evidence of parallel universes, not as science fiction, not as metaphor, but as measurable physical influence, an interaction with something we were never supposed to touch. The idea came from the many worlds interpretation of quantum mechanics. Every time a quantum event occurs, the theory suggests the universe splits. A photon takes one path in this world and the other in another. Every possibility plays out, each in its own version of reality. For decades, the many worlds theory was considered untestable. Elegant, yes. Bold, certainly. But too remote to ever leave the realm of speculation. Then came the plates. The Griffith team used the Casimir effect, an established quantum phenomenon where two closely spaced metal surfaces experience a force from quantum fluctuations in a vacuum. The force is tiny, but predictable. When the plates were aligned under extreme precision, they measured this force again and again. And then, something didn't add up. There were extra forces, anomalies that couldn't be explained by known physics. The deviation was subtle, but statistically significant across hundreds of trials. Nothing in the known quantum field models accounted for the discrepancy. Dr. Howard Wiseman and his team proposed a daring explanation. The plates were being influenced by parallel versions of themselves, running the same experiment in other realities, like faint echoes bleeding across the walls of the multiverse. The idea was breathtaking and contentious. Critics pointed to experimental noise, environmental interference, or unnoticed flaws, but others saw a pattern, a whisper of something vast and previously undetectable. Teams at Oxford University repeated the experiment and reported similar anomalies. MIT's attempts yielded no effect. The inconsistency itself became a clue. If these interuniversal interactions depend on precise conditions, then maybe detection is only possible at certain moments, in certain alignments, like tuning a radio to catch a distant, ghostly broadcast. For a moment, physics stood at a threshold. If the results are confirmed, it would mean that our universe is not alone, that countless versions of reality run parallel to ours, invisible yet real, and that under the right conditions, those versions can touch, just enough to leave a fingerprint on our instruments. What does it mean to live in one world among many? It raises unsettling questions. Are we the original or an offshoot? Do we diverge with every choice we make, splitting into an infinite tree of selves? If other versions of us are out there, what separates them from us, besides chance? And if we can measure the ripple of their existence, are they measuring ours? This is not just a new model of physics, it's a new understanding of identity, of fate, of meaning. A recognition that what we call reality may be one strand in a tapestry too vast to grasp. The Griffith experiment remains controversial, but it reminds us that the line between science and mystery is not fixed. It moves as our questions deepen. And sometimes, reality answers not with certainty, but with a soft nudge, an unexplained force between two plates, in a quiet lab, in one universe among countless others. It started not in the lab, but in the mind. In 2018, at a research facility in California, physicists and neuroscientists joined forces to ask a question that had hovered uneasily over quantum theory for decades. Can human consciousness influence the physical world at the quantum level? For years, quantum mechanics had dodged the question. The famous observer effect, where particles behave differently when measured, was often misinterpreted. In standard models, observation simply meant any interaction with a measuring device, not necessarily a conscious act. But what if consciousness mattered more than anyone wanted to admit? To explore this, researchers used quantum random number generators, devices that produce completely unpredictable sequences based on radioactive decay or vacuum fluctuations. These systems are deeply random. No pattern, no influence, or so it was believed. Volunteers were asked to focus their attention on the machines with one goal: to influence the output toward a specific bias. No touching, no interference, just thought. And the numbers shifted. The change was small, fractions of a percent, but consistent, statistically significant. When conscious intention was focused, the randomness wasn't entirely random anymore. Order crept in. Dr. Dean Radin, who led the experiment, described it carefully. We're not saying mind controls matter. We're saying that under certain conditions, intention seems to correlate with changes in quantum systems. That correlation is hard to explain by chance. The effects were strongest when subjects were emotionally engaged and neurologically synchronized, when their brainwave patterns showed coherence. The more focused and aligned the minds, the stronger the shift. It wasn't the first time such results had been reported. The Princeton Engineering Anomalies Research Lab had documented similar findings for decades, ignored or dismissed by mainstream science. But now, with tighter controls and advanced equipment, the evidence returned, harder to deny. Some dismissed the results as statistical flukes or subconscious biases. But replication efforts, some successful, others not, only deepened the mystery. If the effect was real, it didn't behave like other forces. It was slippery, conditional, dependent on states of mind no equation could yet quantify. And that raised a quiet, startling possibility. What if consciousness isn't just a byproduct of the brain, but a fundamental participant in reality? What if, at the quantum level, awareness plays an active role, not just watching the world, but shaping it? This wasn't about psychic powers or wishful thinking. It was about redefining the boundary between observer and observed. If the act of focusing attention, even briefly, can tilt a quantum process, then something profound is at work. Something that suggests consciousness is not outside the system, but embedded within it. Dr. Stuart Hameroff proposed a radical idea that the brain itself is a quantum system, that consciousness arises not from neurons firing in classical patterns, but from quantum coherence within the very structure of cells. It's a bold theory, not universally accepted, but it points toward a bridge, a place where physics and awareness meet. Not as metaphor, but as mechanism. We still don't know what consciousness is, but perhaps the better question is what it does. And if it does something, even a little, then the universe may not be indifferent after all. It may be listening. And we, in our quiet moments of focus, might be doing more than observing. We might be participating in the becoming of the world. It began with a flicker between ground and sky in 2020. High above the Earth's surface, Chinese scientists performed an experiment that once belonged only to science fiction. Quantum teleportation. Not of bodies or objects, but of information, of the most delicate essence of a particle's identity, sent across space with no medium in between. From a station in the Gobi Desert, they launched pairs of entangled photons, one sent to a satellite orbiting 1,400 kilometers above, the other kept on Earth. What they accomplished would ripple through the world of physics, instantaneous quantum state transfer from ground to orbit. No wires, no waves, no signal passed through the air. And yet, the information was there, faithfully reproduced. The photons were entangled, meaning their states were intertwined across distance. Measure one, and the other adjusts, regardless of space between them. When the team on Earth altered their photons, the satellite's counterparts reflected those changes instantly. It wasn't the particle that traveled, it was its quantum state, its configuration, its probability cloud, its essence. Teleportation, stripped of its cinematic imagery, became something even stranger. It wasn't about movement, but replication, not transportation, but transformation elsewhere. Professor Jianwei Pan, who led the project, was clear. Quantum information can be transmitted across cosmic distances without time delay. The implications shattered previous limits. Information, it seemed, didn't need a path. It didn't move through space. It leapt across it, or bypassed it entirely. Einstein had insisted that nothing could move faster than light. But quantum entanglement doesn't move at all. It connects in a way that defies not just speed, but distance itself. Other teams had achieved teleportation over smaller ranges, 143 kilometers, 10 kilometers, even across buildings. But this was something else, a link between Earth and space, where the quantum connection held steady against gravity, atmosphere, and motion. The fidelity, the accuracy of the transfer remained above 80%, enough to prove the process worked, enough to redefine what communication might mean. The applications were dazzling. Unbreakable encryption, instant messaging across continents, networks of entangled particles enabling quantum computers to talk across space. But beyond the technology lay something deeper. If a particle's identity can exist apart from the particle, what does that say about identity itself? If states can be transmitted without passage, what does that say about presence? And if quantum systems can remain bound over thousands of kilometers, what boundaries truly exist? Entanglement hints that the universe is not made of separate pieces, but of relationships, threads of connection that stretch invisibly through space and time. The experiment didn't just link particles. It revealed that separation might be an illusion, one useful for survival, but inaccurate at the deepest level. We are used to thinking in terms of locations, of here and there, of this and that. But the quantum realm doesn't obey those rules. It suggests that the most real things may be the invisible bonds. That what matters, perhaps, is not the object, but the connection it holds. As the satellite passed overhead, receiving information from a lab in the desert below, something fundamental became visible. The universe, beneath its surface, might be woven not from matter, but from entanglement. A cosmos where everything is already touching, already known, already part of a single unfolding event. And we, with our brief signals and questions, are just beginning to speak its language. It began with something that shouldn't move, something that, by all logic, should have been still. In 2016, scientists at Harvard and MIT created what had only been a theoretical curiosity: time crystals. Unlike ordinary crystals, which repeat their structure in space, like the repeating pattern of a snowflake or a diamond, these strange entities repeated in time. They moved without energy, oscillated without input, violated the most basic expectations of thermodynamics: motion without fuel, change without cause, a kind of eternal heartbeat embedded in matter itself. Time crystals were first proposed by Nobel laureate Frank Wilczek as a radical idea that systems could exhibit periodic behavior in time just as they do in space, while remaining in their lowest energy state. It was dismissed for years as impossible. Perpetual motion machines are forbidden after all, fantasies from a more naive era. But nature, it seems, had a loophole. Using a diamond with nitrogen vacancy centers, atomic defects that respond to lasers, the Harvard team coaxed atoms into a quantum state that pulsed at regular intervals, not driven by any external rhythm, but by the internal dynamics of the system itself. They pulsed at half the frequency of the laser input, a fractional resonance, a broken symmetry. This wasn't just a trick or artifact, it was a new phase of matter, one that maintained motion indefinitely without energy consumption. And it didn't violate conservation laws. It obeyed a deeper, less intuitive rule set of the quantum world. Other labs followed. MIT created time crystals using trapped ions. The University of Maryland achieved it with spin chains. Different methods, same astonishing result: persistent oscillation in a system that should have gone still. And these time crystals weren't delicate. They resisted disruption, maintained coherence, held their rhythm. Like quantum metronomes beating beyond the constraints of classical physics, the implications were staggering. If matter can repeat in time without energy, what else might endure in ways we've never imagined? Could time crystals be harnessed for quantum memory, fault-tolerant computing, or new forms of energy storage? Or were they offering something more fundamental, a window into the hidden architecture of time itself? What is time anyway? We treat it as linear, irreversible, measured by clocks. But at the quantum level, time becomes a parameter, not a substance, a dimension in which patterns can form, echo, persist. Time crystals suggest that time, like space, can be structured, that some things are not just in time, but of it. They challenge our intuition that all motion must come at a cost, that everything winds down, that stillness is the final state. Instead, they whisper another possibility, that beneath the decay of the visible world, something eternal pulses on. That rhythm is not imposed but intrinsic, that some forms of order emerge not from force but from resonance, and that maybe, just maybe, the universe contains not just matter and energy, but choreography, a hidden dance that continues quietly regardless of whether anyone is watching. In the cold laboratories where these time crystals were born, the silence was broken, not by sound, but by rhythm, not by heat, but by motion. A reminder that time may hold more than aging and endings. It may hold patterns that never fade, structures that defy decay, and secrets that reveal themselves not through stillness, but through the quiet persistence of motion where none should exist. It started with a molecule, not a particle. In 2019, researchers at the University of Vienna did something that had long seemed impossible. They coaxed a molecule containing more than 2,000 atoms into a state of quantum superposition. Superposition, the ability of a quantum system to exist in multiple states at once, is often reserved for the tiny, a photon passing through two slits simultaneously, an electron spinning both up and down. These were the comfortable domains of quantum weirdness, safely tucked away from our macroscopic world. But this molecule, a heavy, complex organic structure, defied that separation. The Vienna team used laser cooling and magnetic fields to isolate the molecule, then guided it through a complex interferometer, essentially a device that lets particles take multiple paths at once. The result? Interference patterns emerged, proof that the molecule hadn't chosen a single route. It had traveled all of them, at once. The boundary between quantum and classical had just moved. For years, physicists assumed that as systems grow larger and more complex, quantum behavior would fade. Decoherence, interference from the environment, would wash out the weirdness, forcing particles to choose a state. But the Vienna experiment said otherwise. With enough isolation, enough control, even large molecules could remain in limbo, neither here nor there, but both. It was as if reality, under precise conditions, could be paused in indecision. Soon, other teams pushed further. At Stanford and MIT, experiments approached superposition, with crystalline structures made of tens of thousands of atoms. The quantum curtain was lifting, slowly, into the world of the visible. What does this mean? It means that the strangeness of quantum physics, the duality, the uncertainty, the multiplicity, doesn't end at the microscopic scale. It keeps going. Perhaps one day to systems as large as cells or living organisms. If a molecule can exist in many states at once, Can a brain, a choice, a self? Dr. Marcus Arndt, who led the Vienna research, called it a fundamental shift in how we think about matter. It suggests that the classical world we know, the world of definite outcomes, is not separate from the quantum realm. It is built on it, emerges from it, and perhaps it never truly leaves it. That raises haunting questions. If quantum states persist in large systems, are we also partially unmeasured? Do we collapse into certainty only when watched? Could our perceptions, decisions, or thoughts themselves exist in quantum limbo before becoming real? Is the world as we know it a superposition, a blend of possible stories, stabilized only through observation, attention, or memory? We may never fully know, but the experiment forces us to admit what we've long suspected, that the divide between the quantum and the classical is not a wall, but a veil. And under the right conditions, that veil can be pulled back, revealing a universe that never quite makes up its mind, where possibility holds out longer than we thought, and where certainty is not a given, but a choice, made perhaps by us, or by the mysterious unfolding of the universe itself, watching, waiting, and gently asking, what will you become now that you know you do not have to be only one thing? It started with a web, a lattice of invisible threads, stretching farther than anyone had ever managed before. In 2020, physicists at the University of Geneva achieved something extraordinary: the largest quantum entanglement network ever constructed. Over 100 particles, entangled simultaneously, forming a coherent system where a change in one instantaneously influenced the rest. It was no longer just about pairs, not just two photons dancing across space in perfect sync. This was an orchestra of particles, spanning space, locked in quantum harmony. They used trapped ions and electromagnetic fields to weave the entanglement. It wasn't easy. Entangling even two particles requires precise conditions. Entangling 100, that was like trying to conduct a symphony where every instrument must play the same note at the same time, without ever touching. And yet it worked. Any measurement of a single particle immediately influenced all the others, regardless of distance. The web held not for milliseconds but for minutes, an eternity in quantum terms. Dr. Nicholas Kizin, who oversaw the work, described it as a quantum web, a network where every node remained intimately connected, no matter how far apart they seemed. A single alteration rippled through the entire system. This wasn't just a demonstration of skill, it was a revelation, because entanglement had long been understood as a two-party affair, a bizarre but limited phenomenon. What Geneva showed was that it could scale, that complexity was no obstacle, that even in crowded systems, quantum unity could persist. Other teams had achieved smaller networks, 20, maybe 50 particles. But Geneva doubled the scale, proving that entanglement is not fragile, it's foundational. The implications were staggering. In quantum computing, such networks could enable parallel calculations across all nodes at once, exponentially increasing power. In communication, they could create systems where information isn't transmitted, but shared instantaneously, impossible to intercept, impossible to fake. But beyond technology, the experiment pointed toward a deeper truth. That reality is not a collection of isolated pieces, but an interdependent field. That particles don't merely coexist, they co-define. They are not separate, but aspects of a shared state. The universe, it seems, is less like a machine and more like a conversation. What does that mean for us? If every piece of matter is part of a network, entangled, influenced, intertwined, then the idea of pure individuality begins to falter. Our sense of separation may be practical, but not fundamental. We are threads in a web, points of coherence in a field of possibility, participants in something larger than ourselves, whether we recognize it or not. And perhaps that's the quiet truth the quantum world keeps trying to show us, that we are never truly alone, that our actions ripple further than we know, and that beneath the apparent chaos of the everyday lies a deeper pattern, woven not from certainty, but from connection, a vast entanglement, humming quietly beneath reality's surface, waiting for us to listen, not just with instruments, but with wonder. It began with a room full of people, all thinking the same thought. In 2021, researchers at MIT took the quantum observer effect, the principle that the act of observation can influence the outcome of a quantum system, and asked a new question. What happens when many minds observe together? Could multiple conscious observers focusing on the same quantum event create a stronger, more pronounced effect than one person alone? The idea was audacious. Observation in quantum mechanics traditionally referred to interaction with instruments, not minds. But prior experiments hinted that consciousness might not be so easily dismissed. MIT's team decided to test the boundaries. They gathered groups of participants and gave them a task: focus collectively on a quantum system, quantum dots held in superposition, and try to influence it simply by observing, attending, concentrating. What they found was unexpected. The more people who observed the system simultaneously, the faster the quantum wave function collapsed. Superposition states, where particles exist in multiple possibilities, disappeared more quickly under the gaze of many minds than under one. And the effect wasn't just about numbers. It was about synchronization. EEG scans revealed that when participants' brainwaves became coherent, when their neural rhythms aligned, the collapse became more pronounced. Collective attention, especially in shared mental states, appeared to amplify the observer effect. Dr. Seth Lloyd, who led the study, noted, "It's as if the quantum system listens more intently when consciousness speaks in chorus." Skeptics were quick to raise questions. Could it be statistical noise, instrument sensitivity, expectation bias? But replication efforts at Princeton and other institutions found similar trends. The effect varied depending on the observers, their focus, and their emotional engagement. But the pattern was there. If verified, it suggests something staggering: that consciousness is not just an isolated observer, but a force that can act in concert. That collective awareness may influence reality more than the sum of its parts. What does this mean? It suggests that the mind is not simply watching the world, but touching it. That observation, especially shared observation, might participate in shaping events at their most fundamental level, not with intention, not with magic, but with presence. And if that's true, then consciousness is not an epiphenomenon, not just a side effect of biology. It's a participant in the unfolding of the universe. This doesn't mean we control reality. It doesn't mean thought alone can bend the laws of physics. But it does mean that awareness, especially when synchronized, focused, and shared, may be a deeper part of the system than we imagined. It reframes the idea of collective human experience. Meditation, ritual, ceremony, even simple shared attention, watching a sunrise, mourning a loss, standing in silence. These moments may not just be emotional, they may be quantum. Moments when the boundary between inner and outer blurs, when observation becomes participation. And when the universe, at its smallest scales, seems to pause and respond, not to force, but to focus, we often think of consciousness as private, solitary, trapped within skulls. But maybe it's something else entirely. A resonance, a field, a choir, one that when tuned together, echoes not just in minds, but in matter itself. It began with a question as old as thought itself. What is the boundary between mind and matter? For generations, physics kept consciousness at arm's length. Matter could be measured, energy could be quantified. But the mind, it was the domain of psychology, philosophy, perhaps even faith, not science. And yet, experiment after experiment refused to let the question go. From subtle shifts in quantum randomness to synchronized observer effects, patterns emerged, quiet but persistent, suggesting that awareness plays a deeper role than previously believed. Some researchers began connecting the dots. At the University of Arizona, Dr. Stuart Hameroff and physicist Sir Roger Penrose proposed that consciousness arises from quantum processes within the brain, specifically in the microtubules of neurons. These tiny structures, they argued, could sustain quantum coherence long enough to influence thought, decision, perception. The brain, in this view, wasn't just a biological machine. It was a quantum computer, one capable of entanglement, superposition, even non-local influence. The idea was controversial, but it resonated with a growing body of research showing that the mind interacts with physical systems in subtle, statistically significant ways. In recent years, studies have gone further. When researchers stimulated neural patterns associated with focused consciousness, the ability to influence quantum systems increased. Enhanced gamma-wave coherence, patterns often associated with meditation, creativity, or heightened awareness, correlated with stronger quantum effects, and remote influence, long considered fringe, began to yield measurable outcomes. In controlled environments, participants were able to produce small but consistent changes in quantum systems they could not see or touch, using only intention. No one claims to fully understand how, but something is happening at the intersection of mind and matter, something that suggests the observer is more than an external factor, perhaps even more than a participant. Perhaps the observer is a bridge between what is and what might be, between probability and presence. We do not yet have the language to fully explain this, but the implications echo far beyond the lab. If consciousness can influence physical systems, even slightly, then reality is not indifferent. It is participatory. And if it is participatory, then every act of awareness carries meaning. Not mystical, not magical, simply fundamental. What we attend to may shape what unfolds. What we believe may echo more deeply than neurons and culture. What we feel, especially when felt together, may ripple across levels of reality we are only beginning to explore. This is not a call to abandon science. It is a call to expand it, to consider that the mind is not a spectator of the universe, but a thread woven through its very structure. That we are not merely in the world, we are of it, shaping, witnessing, co-creating the dance between particle and wave, cause and effect, choice and chance. And if the universe listens, even faintly, to the quiet hum of awareness, then consciousness is not the end of the equation. It may be where the math begins. It began with 10 experiments, 10 fractures in the mirror of reality. Each one, on its own, might have been dismissed, a curious anomaly, a technical fluke. But together, they formed a pattern, a constellation of impossible truths that refused to stay theoretical. Photons that rewrite their past based on future decisions. Particles that act as one across vast distances. Electrons that cross barriers without taking time to do so. Molecules that exist in multiple places at once. Human minds that seem to tip the scales of probability. Time crystals that oscillate forever. Entanglement webs that ripple beyond separation. Consciousness not as a side effect, but as a subtle force. Each experiment came with instruments, data, replication. These were not dreams, they were numbers, confirmed in labs from Vienna to Beijing, from MIT to Geneva. And yet the results felt more like philosophy than physics, because they didn't just challenge our models. They challenged our assumptions about time, about space, about what it means to exist. The universe, once imagined as a vast machine, revealed itself to be more like a poem, fluid, relational, recursive, less made of things and more made of interactions. Less a stage, more a conversation. We learned that the past is not always fixed, that distance is not always real, that observation is not always passive, that reality waits for something, for a measurement, for a decision, perhaps even for attention. The quantum world is not far away. It is not confined to the small. It underlies everything. It shapes the ground we walk on, the thoughts we think, the very conditions under which real becomes real. It whispers that cause and effect are not as linear as they seem. That information may be more fundamental than matter, that the mind is not an intruder, but a native inhabitant. These are not metaphors. They are consequences, testable, repeatable, bewildering consequences. And the more we learn, the more we're forced to confront a question no equation can answer. What kind of universe behaves this way? A universe where particles wait for choices that haven't yet been made. A universe where entangled photons defy distance, where matter sustains motion without energy, where randomness bends in the presence of consciousness. A universe that seems aware, or if not aware, at least responsive, tuned, relational in a way that defies classical imagination. Perhaps reality is not a cold engine, but a warm field, not indifferent, but participatory. Perhaps it is less about what is and more about what might become. Through interaction, through intention, through observation, we stand at the edge of something vast, not the end of science, but the beginning of a deeper kind, one that honors both logic and mystery, one that admits we are no longer outside the system we study. We are inside it, entangled with it. And as the data keeps showing us, we are far more connected to each other, to the cosmos, to the very roots of being than we ever imagined. The question now is not whether this is real. The question is what we will do with the knowing. It ends where it began, with a question. What is reality, truly, when the ground beneath our assumptions gives way? We once believed in a clockwork universe, solid, predictable, governed by laws that mirrored the logic of machines. But the closer we looked, the more those gears dissolved. Certainty blurred into probability. Objects became patterns. Time lost its arrow, and at the smallest scale, observation itself changed the outcome. These weren't philosophical musings. They were results, verified, replicated, peer-reviewed. From quantum erasers to time crystals, from superposition to teleportation, the experiments left us with no clean answers, only deeper, more beautiful questions. If the future can influence the past, what does it mean to remember? If two particles can remain linked across galaxies, what does it mean to be separate? If a thought, a moment of consciousness, can influence the very randomness of nature, then what are we? The old lines between observer and observed, between mind and matter, between cause and effect, are fading. In their place emerges a tapestry more strange and more human than we anticipated. We are not spectators on the sidelines of the universe. We are participants, co-creators in a reality that does not merely unfold, but responds. Not because it knows us, but because it includes us. Physics is not done. Far from it. We will build better instruments, craft tighter theories, rewrite equations. But the lesson of the quantum realm is not just technical, it's existential, that at its heart, the universe is not built from things. It's built from relationships. And in those relationships, between particles, between people, between questions and answers, something sacred persists. A dialogue between what is and what might be, between curiosity and wonder, between silence and discovery. This series has traced 10 experiments, but really, it has traced one journey, the unraveling of certainty and the birth of a new kind of knowing, one that does not demand belief, only attention, only humility, only the courage to keep asking, because perhaps the universe, in all its strangeness, is not here to be solved. Perhaps it is here to be met. And if we meet it fully, open-eyed, open-minded, then maybe the greatest discovery is not how the universe works, but that it has always been waiting for us to notice that we were never separate from it at all. Not even for a moment. Not even for a particle's breath of time.